Hello and welcome back to Linear Models with Matrices. The last module was all about estimating the regression coefficients and working out their sampling variance or sampling distributions. This one's going to start out talking about estimation of the other parameter in the model, which is the variance parameter, sigma squared. And we're going to use that to talk about how to construct the t-test and also the f-test. So let's jump into it. So you've probably seen this formula, sigma hat squares equals, in the numerator you have the residual sum of squares, so response data yi minus fitted value yi squared added up. And then you divide by n minus p minus 1. So remember that p is the number of covariates in the model, and you have an intercept as well, so the dimension of the design matrix is going to be n by p plus 1. And so basically what you do is you subtract off n minus the rank of the design matrix when it's full rank. So the question is, this is an estimate, and we want to perhaps do hypothesis testing for this parameter, sigma squared, which means we have to work out its sampling distribution. And we'll also address this question of why do we divide by n minus p minus 1 instead of, for example, dividing by n, which is the number of terms in the numerator. Okay, so let's look at this residual sum of squares, and we're going to write it out in terms that allow us to do something with it. So if we take this thing, it looks like we're taking a vector y and we're subtracting off the fitted value vector y hat. So we're going to write that over here. And when you do this sum of squares, another way of writing that is to take that difference, take its transpose, and multiply it by itself. So if you take this expression and write it out in terms of the individual elements of these vectors, you're going to get this thing in yellow on the left here. Now, if we recall what the formula for y hat is, it's just the projection matrix times y. So that's just plugging that in there. And then if I look at this expression, y minus py, well, that we can write as a matrix vector multiplication, namely I minus p times y. So if you expand this out, you're going to get I times y is y, minus py is y. And then the other thing is just the transpose of that, so we're just taking the transpose here. And then if we distribute this transpose, we get y transpose I minus p transpose times I minus p. And recall that if p is a projection matrix, then so is I minus p. And so I minus p must be symmetric and idempotent. So you can take this transpose away, and you get I minus p times I minus p, and then use the idempotent property to get it's equal to this, y transpose I minus p times y. Okay, so if we want to work out, so this thing, just to recall, this is the thing that's in the numerator of the formula for the estimate of sigma squared. So if we want to work out the sampling distribution of sigma hat squared, we have to look at the sampling distribution of the random variable version of this thing because, well, this is the important part because the rest of it you're just dividing by a non-random quantity. So we need to study this random variable, the random variable version of y, transpose times I minus p times y. Okay. So let's recall one of our facts about projection matrices. One of the facts is that if we have any projection matrix, we can write it as Z transpose, where there's some special facts about Z. So Z has orthonormal columns, and the span of the columns of Z is equal to the span of the projection matrix. Okay, so that's the first thing. Which means that if we take this thing y transpose I minus py, we can rewrite it as y transpose Z times Z transpose Y. And of course, we can rewrite it this way. And then I'm just going to define z transpose y to be this vector capital V. And then we're going to study this vector capital V. So this vector capital V is just a matrix, Z transpose, times a multivariate normal vector. Therefore, V itself is multivariate normal. Let's quickly look at the dimensions of V. So Z is going to be n minus p minus 1 by, let's see, yeah, n minus p minus 1 by n. Y is n by 1. So V is going to be n minus p minus 1 by 1. And since it's multivariate normal, we just need to work out its expected value and its covariance matrix. So if we look at expected value of V, we get expected value of Z transpose Y. The Z transpose is not random, so that comes out. So you get Z transpose expected value of Y, which is XB. And one thing to remember is that if we do Z transpose X, we're going to get 0. One of the reasons is that the span of I minus P is going to be orthogonal to the span of P, which is the same as the span of X. Another way of seeing it is to just do the algebra, and you'll get something like X minus PX, and that's 0. So that's another way of seeing it. But you can also see it by just knowing that the span of Z is orthogonal to the columns of X. So if you do any column of Z dot product with any column of X, you're going to get a 0. So this expected value of Z has to be 0 because it's 0 times B. Okay, so that's the first fact. The other fact, we're going to look at the covariance matrix for V. So we'll just use our properties of linear transformations of random variables, the covariance of them. So this just becomes Z transpose times the covariance of Y with itself times Z. And so this is Z transpose sigma squared I, which is the covariance matrix for Y, times Z, which is just sigma squared times Z transpose Z. And remember, Z is an orthonormal, has orthonormal columns. So this just becomes sigma squared. And importantly, let's keep track of the dimensions of this identity matrix. It's sigma squared I sub n minus p minus 1. So that's going to be important. It's a n minus p minus 1 by n minus p minus 1 identity matrix. All right, so putting this together, we get V is normal, mean 0, and sigma squared I covariance matrix. What that means is if we take each entry of V and we divide it by sigma, so each entry of V is independent of all other entries, and its variance is sigma squared. So if we take each entry of V and divide it by sigma, this thing is just going to be a standard normal. And so is this one. So each entry of V divided by sigma is a standard normal, and they're independent because the covariance matrix is this identity. So you have this, the entries of V divided by sigma are independent normal 0, 1, which means that if you square them and add them up, you might recall that the square of a normal 0, 1 is a chi-squared, and then chi-squared with 1 degree of freedom. And then the sum of the square of a bunch of independent normal 0, 1s is a chi-squared equal to the, with degrees of freedom equal to the number of things that you added up. So if we look at this quantity, this ends up being sum Vi over sigma squared. I equals 1 to n minus p minus 1. And it has to have a chi-squared distribution with n minus p minus 1 degrees of freedom. Okay, so this is where this n minus p minus 1 thing comes from. It all stems from the fact that this matrix that appears inside of what's called a quadratic form, so this quantity is called a quadratic form, the rank of this matrix, which is equivalent to saying the dimension of the span of I minus p is n minus p minus 1. So that's where this comes from. And then if we put all this together, remember that, so we're talking about V transpose V, which is equal to this Y transpose I minus PY, which is the thing that appears in the numerator. So if we take this sigma hat squared, we divide it by sigma, which here, sigma squared, and then we multiply it by n minus p minus 1 to make this go away. We get that this quantity is a chi-squared n minus p minus 1. Okay, so this is a little bit, I won't say it's weird, but it's kind of a little bit different because the parameter, to make this distribution nice, the parameter appears on the left side. But it's not really complicated. So, for example, if you wanted to do a hypothesis test for sigma squared equals 12, I'm just picking a number, we form our statistic, which is going to be sigma hat squared divided by the hypothesized value of sigma squared multiplied by n minus p minus 1. Under the null hypothesis, this thing has a chi-squared distribution with n minus p minus 1 degrees of freedom. And so you just have to take this thing and compare it to this chi-squared distribution. So for example, if this thing is much larger than what is expected under this chi-squared distribution, then you'll reject the null hypothesis. And same thing, if it's much smaller, then you'll also reject this null hypothesis. So this is maybe a bit different than you've seen, that the parameter appears in the statistic, but it's really not. Once you hypothesize a value, then you actually have a value here. So it's not really that complicated. So this is the test statistic. All right, next we'll move on to hypothesis testing for regression coefficients, which turns out is actually a slightly harder problem, but it's not too complicated. So again, here's the model. Random vector y equals xb plus epsilon, where epsilon is multivariate normal, mean 0, covariance matrix sigma squared I. So this implies that the y's all have the same variance and are independent of one another. Okay, so often our question of interest can be formulated in terms of this model as something like the hypothesis H naught is that b sub j, one of the regression coefficients, is 0, or some other number than 0. So for example, if we were doing a regression on child height, so child height on parent's height and maternal grandmother's height, if we were testing the hypothesis that the maternal grandmother's coefficient was 0, we would be trying to answer the following question. Does maternal grandmother height affect child's height after controlling for both parents' height? So clearly there should be a correlation between maternal grandparents' height and grandchild's height. But this is a different question. Does knowing the maternal grandmother's height provide any additional information after knowing the two parents' heights? Okay, so we're interested in questions like this, and testing this hypothesis, on the other hand, is designed to answer questions like this. All right, so how does hypothesis testing work? In general, you need to come up with a test statistic and derive its sampling distribution under this null hypothesis. So let's think about some candidates. If we look at the random version of that estimate of the regression coefficient, it has this distribution. So b hat j is distributed as normal, mean 0 under the null, and this is the sampling variance. So we work this out. You look at the sigma squared times the inverse of x transpose x, and the entry that we're interested in is the j plus 1 comma j plus 1 entry of that inverse. Reason for that is that the first entry corresponds to b sub 0, second entry is b sub 1. Okay, so this as a candidate for the sampling distribution, this is the sampling distribution, but we can't use this one as a test statistic because it contains information in the distribution that we don't know, namely sigma squared. So we need to estimate sigma squared. We would need to know sigma squared to use this sampling distribution. So one alternative would be to plug in our estimate and use this. But this isn't quite satisfactory because this thing doesn't actually have this distribution because sigma hat squared is not generally equal to sigma squared. Now we could think of this as the random variable version of this, but that's also a problem because now we're thinking of b hat j as normal mean zero with a random variance, which I don't even know how to think about. So another candidate, and this is the one, the test statistic that we end up using, is the following: b hat j divided by this quantity here. So this quantity here is this quantity here. And let me just tell you that we're thinking of sigma hat squared here as the random variable version of sigma hat squared. So we're taking this random variable and dividing it by the square root of this random variable times x transpose x inverse j plus 1, j plus 1. Now the question is, what is the sampling distribution of this random variable? This is clearly a random variable because it involves random things, but it's kind of a weird one because there's a normal on the top, but then there's like a square root of this thing which has like a chi-squared distribution. So this is going to be a weird distribution, but it's one we know about. So let's derive what it is. Okay, so let's turns out it's going to have a t-distribution. So what we're going to start with is I'm going to define what the t-distribution is, and then we're going to verify according to this definition that this test statistic has a t-distribution. All right, so what is the t-distribution? If we have z, a normal 0, 1 random variable, and then we have a separate random variable w, which is distributed as chi-squared m, so m is going to be the degrees of freedom, and additionally, z is independent of w, then the following quantity has a t-distribution with m degrees of freedom. And the quantity is z divided by the square root of the quantity w divided by its degrees of freedom. All right, so the strategy we're going to follow here is we're going to build up this test statistic, and we're going to verify that it adheres to the rules for the t-distribution. Okay, so let's start here. I'm going to try to have this all on the same screen. So we'll start here. We know that b hat j, normal, means 0 under the null. Remember, the null hypothesis is that b sub j is 0 in this particular case. And its variance is the following. Again, we don't know sigma squared, but it turns out that's not going to be important here, and we'll see why. So if we take b hat j and divide it by its standard deviation, which is just the square root of its variance, then this quantity here has a normal 0, 1 distribution. This is just because if you take a normal mean 0 and divide by its standard deviation, you'll automatically get a normal 0, 1. Okay, an additional piece of information. Remember from a couple of pages back that the random variable sigma hat squared divided by sigma squared multiplied by its residual degrees of freedom has a chi-squared distribution with n minus p minus 1 degrees of freedom. All right, so let's form the following thing. So it's going to have a numerator and a denominator. In the numerator, we're putting b hat j divided by square root sigma squared, blah, blah, blah. So this thing in the numerator has a normal 0, 1. Okay, so we're on the right track because z has a normal 0, 1 in the t-distribution. And in the denominator, we're going to put the following. We're going to do this thing, which has a chi-squared n minus p minus 1, But additionally, we're going to divide by n minus p minus 1. So you can see why we're doing this. In the t distribution, you start with a w, which has m degrees of freedom, and you divide by its degrees of freedom. So we're starting with this thing, which has chi-squared n minus p minus 1 degrees of freedom, and we're dividing by that degrees of freedom. Okay, so this has the right form. It's got a normal 0, 1 on the top. It's got a chi-squared divided by its degrees of freedom in the bottom. And if you look at this, the sigma squareds, well, first n minus p minus 1s cancel, obviously, but the sigma squareds also cancel. And if you pull this down into the denominator, you're going to get sigma hat squared times x transpose x inverse j plus 1 comma j plus 1, which is exactly the candidate that we're talking about here. So we've almost done all the steps to show that it's a t distribution. We've shown that this thing here is a normal 0, 1 divided by a chi-squared square root of a chi-squared divided by its degrees of freedom. But remember, back to the definition of the t, there's one additional thing that you have to show, and it's this here, that the normal 0, 1 is independent of the chi-squared. So that's what we're going to do next. Now, this is a bit of a long derivation, as you can see, but let me lay out what the strategy is going to be. The sigma hat squared is constructed from the residual vector. So it's just the squared length of the residual vector divided by n minus p minus 1. So, and it turns out that we know that the residual vector has a multivariate normal distribution, and the regression coefficient estimator has a multivariate normal distribution. And if you have two multivariate normals, and those two multivariate normals are uncorrelated with each other, what we mean by that is that every element of b hat is uncorrelated with every element of e hat, then these two things are independent. And additionally, what independence means is that additionally any function of these two things are independent of one another. So that means that b hat, if b hat is independent of e hat, then b hat j is going to be independent of sigma hat squared, because sigma hat squared is just a function of epsilon. So this all boils down to showing that b hat and e hat are uncorrelated. Okay, so let's compute their covariance and verify that. I'm not going to go through all the steps of the derivation, but I'll take you through the first couple. The rest of it's just manipulating formulas here. So one formula for the covariance is you take the expected value of the first thing times the second thing transpose. Remember that this is going to be a p plus 1 by n matrix. It's a cross covariance matrix. And you subtract off the expected value of b hat and multiplied by expected value of e hat transpose. Okay, now the first thing to notice is that expected value of e hat is 0. This is the residual vector, so it has expected value 0. So this term, the second term, goes away, and we just have to look at the first term. The first term has b hat and e hat transpose, so b hat is just the following: x transpose x inverse x transpose y. And e hat is the following: I minus p times y. Remember, this is just y minus the fitted values, which is py. And if you rearrange things, we could skip this step. This is just a rearrangement. You get something that looks like this. So some x's over here, some I minus x's over here, but in the middle is expected value y transpose. And remember that the expected value of y transpose is its mean times its mean transpose plus its covariance matrix. So once you have it into this form, then it's just about manipulating equations, and you do a bunch of x transpose x inverse times x transpose x equals identity, and then you can see that you get down to something that's 0 at the end. So if you go through all these steps, you can show that B hat and E hat are uncorrelated, and therefore, because they're multivariate normal, they're independent, and any function of them are also independent. Okay, and that's just the argument that's laid out here. The residuals are uncorrelated with the regression coefficients. Both are multivariate normal. Therefore, uncorrelated implies independent. And if two things are independent, then any function of them are independent as well. So B hat J is independent of this function of the residuals, and this is precisely sigma hat squared. Okay, one thing to note that in general, uncorrelated does not imply independent. But if you're working with multivariate normals, then that is true. Uncorrelated does imply independent. Okay, so taking all this together, that means that we verified the three things, that this quantity is a normal 0, 1 divided by a square root of a chi-squared divided by its degrees of freedom, and the normal 0, 1 is independent of the chi-squared, and therefore this has a t-distribution. So the way we do testing is we form this statistic from the data. Notice I'm using a lowercase t here because this is the estimate, and this is also the estimate now. And compare this thing to a t-distribution with n minus p minus 1 degrees of freedom, which of course you already knew that's what you're supposed to do, but now that we're in this advanced course, we're actually verifying that this is the right distribution. Okay, another thing about t-tests is they can also be used to test hypotheses that have the following form. So if we have some vector c, that's p plus 1 by 1. And we compute c transpose b. So this is just a linear combination of the regression coefficients. We can test the hypothesis that c transpose b equals some quantity. The reason for this is because c transpose b hat is just a linear combination of entries of a multivariate normal. So therefore, this thing has a normal distribution. Subtracting off its hypothesized value, and then we're dividing by the right thing to make this have a t-distribution. And it turns out that the right standard error to divide by is just the variance of this quantity. And remember, back when we talked about properties of the multivariate normal, we know that B hat is its covariance matrix is sigma squared x transpose x inverse. And therefore, if we do a vector times B hat, the covariance matrix for this thing is going to be C transpose x inverse times C. And it turns out that this is a scalar, or you could think of this as a 1 by 1 matrix. And this is the more general form. What I mean by that is that the t-statistic that we talked about first is just a special case of this kind of t-statistic where C has a 1 in the j plus 1 entry and A is equal to 0. So if you set C equal to this and A equals to 0, you get T equals B hat J divided by x transpose x inverse j plus 1 comma j plus 1. All right, so that means you can use the t-distribution to do hypothesis testing with linear combinations of the regression coefficients. However, we cannot use the t-test to test hypotheses such as the following, that this regression coefficient B1 is 0 and this regression coefficient B2 is 0. So this is a different type of hypothesis that cannot be written as C transpose B equals 0. So for that, we need a different kind of test, and that's the F-test. So let's go back to our parent, grandparent, grandchild height example. So here yi is the ith child's height, and our covariates are, the first two are that child's parents' heights, and the next four covariates are the grandparent heights. And we want to know, so you probably heard like folklore, that certain traits skip a generation, meaning that knowing something about the grandparent tells you something about the grandchild that's not contained in the information about the parent. So maybe we want to test that sort of folklore. So in this case, we'd want to test that there's no information in the grandparent heights after controlling for the parent's heights. And it turns out the right hypothesis there is that B3, B4, B5, B6, which are the grandparent height coefficients, are all equal to 0. And the alternative here would be that at least one of those coefficients is not 0. So what would be a reasonable test statistic? It's kind of hard to come up with something because it's not like, so B3 equals 0, or you could test that by doing, looking at B hat 3 and comparing that to its standard error, but that wouldn't say anything about the other ones. So we need something different here, and that's the different thing that we need is the F-test. So in this case, what I'm going to do is I'm going to write down the procedure for doing the F-test, and then we'll verify that the statistic that we use has an F distribution. Okay, so here's the procedure. We write down two models. The two models we call the reduced model and the full model. The reduced model is the model that is implied by the null hypothesis. So in this case, the null hypothesis is that all four of these coefficients are 0. So if we apply that hypothesis to this model, we get yi is just sum j equals 0 to 2, xij bj plus epsilon I. The full model is just the model, which allows the grandparent coefficients to be non-zero. And so this is just the first model that we wrote down. So called this the reduced model and the full model. The procedure is that we fit both models and we collect certain information from those models. We need the residual sum of squares from the null model, the reduced model. We'll call that RSS0. We need the model degrees of freedom from the null model. In this case, that's 3. Unless there's something weird going on with the design matrix, then the design matrix should have rank 3. And then we need the same quantities from the full model. We'll call it residual sum of squares 1 and model degrees of freedom 1. In this case, that's 7. Again, assuming there's nothing weird going on with the design matrix, it should have rank 7. Then from this information, we can calculate residual degrees of freedom for both models. But we're going to write the statistic in terms of model degrees of freedom. All right, and here's the F statistic. We take the difference between the reduced model degree sum of squares and full model sum of squares, divide that quantity by the difference in model degrees of freedom, and then divide the whole thing by what turns out to be the variance estimate from the full model, which is equal to residual sum of squares full model divided by its residual degrees of freedom. So that's the statistic, and what we have to do is work out its sampling distribution. But before we do that, let's think about what this statistic is measuring and what values of the statistic constitute evidence against the null hypothesis. Okay, so I'm claiming that a large F statistic constitutes evidence against the null. Why is that? So I'm trying to keep everything on the same page here. So let's look at the first quantity, RSS0 minus RSS1. What this measures is how much does the residual sum of squares go down when you switch from the null model to the full model. Okay, so the residual sum of squares in the null model is RSS0, and when we add the grandparent covariates to the model, the residual sum of squares has to go down, and this measures how much it goes down. Okay, so that's the first quantity. We divide that quantity by MDF1 minus MDF0. So what does this measure? This is a measurement of how much more complex the full model is than the reduced model. So what I mean by that is the full model has 6 covariates, and therefore the model degrees of freedom is 7. The reduced model only has 2 covariates, and therefore its model degrees of freedom is 3. And so 7 minus 3 measures how much more complex is the full model than the reduced model. So if we look at the numerator of the F statistic, this measures the amount that the residual sum of squares goes down when we switch from the reduced to the full model, scaled by how much more complex the model got when you switch from the reduced model to the full model. So this is the numerator here is like a scaled reduction in sum of squares by the increase in the model complexity. Now we divide the whole thing by the estimate of the variance in the full model. The reason for this is to make the F statistic a unitless quantity, so that we can get a number and be able to kind of interpret that without reference to some unit. So for example, if we were measuring heights in inches, we get an F statistic. We want that to be the same F statistic that we would get if we were measuring heights in centimeters, because the choice of units should not influence the conclusions that we make here. Okay. So that's just a heuristic idea of what this F statistic is measuring. But in practice, what we actually need to do is we need to compare F to its sampling distribution to get a p-value. So it turns out it's going to have an F distribution, but we're going to use the same strategy here. First, I'm going to tell you what the F distribution is, and then we're going to verify that the F statistic that we constructed actually has an F distribution. Okay, so what is the F distribution? If we construct a random variable in the following way, we do W1 divided by M1, where W1 has a chi-square distribution with M1 degrees of freedom. And we divide that by W2 divided by M2, where W2 is a different chi-squared with M2 degrees of freedom. And the two chi-squares are independent. Then that quantity has an F distribution with M1, M2 degrees of freedom. We'll normally call M1 the numerator degrees of freedom and M2 the denominator degrees of freedom for obvious reasons. Okay, so does this apply to our F statistic that we've constructed? Well, let's look at it. So if we look at the denominator, this looks okay. So we already know that this residual sum of squares has a chi-squared distribution, and we're dividing it by its degrees of freedom. There's some extra stuff here, a sigma squared that's hanging out here, but turns out that's going to cancel out when we actually construct it. So the denominator actually looks okay. The numerator is a little bit weird. We know that RS is 0 under the null is going to have a chi-squared distribution subject to some constants. But we're actually looking at the difference between these two and dividing it by the difference in their degrees of freedom. So it's not so obvious that the numerator is going to have a chi-squared distribution. So we need to check that, and we need to check that the numerator is independent of the denominator. All right, let's get into it. So to verify the things that we want to verify, we're going to need some new notation. So let's define X0 to be the design matrix under H0. So in this maternal or grandparent example, that's just going to be the first 3 columns of the design matrix. And let's define X1 to be the design matrix under the alternative, which would be the entire design matrix. Then from these two things, we can define the following projections. So P0 is going to be the projection onto the column space of x0. And P1 is going to be the projection onto the column space of x1, where x1 is the full design matrix which contains x0. So because these are both symmetric idempotent matrices and their projections, we can write each of them as a matrix times a matrix transpose, where that matrix has orthogonal columns. So we can write P0 as U0, U0 transpose, where U0 obviously has n rows, but it has the number of columns equal to the rank of x0. And P1 and U0 spans the same, the columns of U0 span the same space as P0 and they're orthogonal. Now, for P1, we could do something a little bit interesting here. Because x naught is a column, the column space of x naught is a sub space of the column space of x1, we can write P1 with vectors that span the column space of x1, but that contain the same spanning vectors that we used to span x0. So we can write P1 as U0, U1, where U0 are the vectors we use to span x0, and U1 are whatever additional vectors we need to span x1. So P1 is U0, U1, U0, U1 transpose. Now, one notational thing. So in our grandparent example, x1 will have 7 columns. x0 has 3 columns. Here, U0 has 3 columns. U0 has 3 columns. And U1 will have 4 columns, one for each additional covariate. All right. Now, U0 and U1 are orthogonal by construction because if we take this projection matrix and we write it down in terms of orthogonal columns, any of the columns are orthogonal of any of the others. So all of the columns in U1 are orthogonal to all the columns in U0, meaning that the following is true. U0 transpose U1 equals the 0 vector. As we said before, this is constructed so that the span of U0 is the same as the span of x0, and the span of this augmented matrix U0, U1 is the same as the span of x1. Now, just to dive back in this for a second, what we're interested in is learning about the distribution of RSS0 minus RSS1. So RSS0 we can write this way. This is the sum of squared residuals for the reduced model. We can write it in this form. RSS1 you can write like this in terms of P1. And therefore the difference, RSS0 minus RSS1, is the following. And then if we collect things, we see we get I minus I, so that goes away. And then we get P1 minus P0. So this difference in sums of squares we can write as Y transpose P1 minus P0Y. Now the question is this thing going to have a chi-squared distribution? And so what we need to check is this thing a symmetric idempotent matrix? And if we do this thing times x under the null, do we get 0? Okay, so let's do symmetric first. That's the easy one. Both P1 and P0 are symmetric, so their difference is symmetric. Now, let's look at whether it's idempotent. So this is how we check whether it's idempotent. If we write this out, if we FOIL it, we get P1 minus P0 P1 minus P1 P0 plus P0. And then we're going to look at these individual terms. So if we look at P0 P1, we get the following. This is P0 and this is P1. If we write this out, we have U0 and we distribute this U0 transpose. We get U0 transpose U0 and U0 transpose U1. So that's U0, this thing times this thing, and then we're leaving this alone. Now if we inspect this thing, U0 transpose U0 is the identity matrix. And as we said before, U0 transpose U1 is 0. So we're left with U0 times I0. And then we take the transpose of this, we get U0 transpose U1 transpose. If we write this out, if we multiply these second two matrices together, we get U0 times I U0 transpose plus 0 U1 transpose. So this is obviously U0 transpose. And putting everything together, we get that this is equal to U0 times U0 transpose. So P0, P1 is U0, U0 transpose, which is P0. Okay, so that means that this thing we can replace with P0. So this is going to cancel with that. And now let's just look at P1, P0. Well, P1, P0 is equal to the transpose of P0, P1. This is an easy little trick here. So if we can rewrite P1, P0 as P1 transpose, P0 transpose. That's because they're symmetric. So P1 equals P1 transpose. And then P1 transpose, P0 transpose is equal to the transpose of P0, P1. And then on the inside, we've written it in terms of something we already know. So on the inside is P0 transpose, and P0 is symmetric, therefore it's P0. So this one we can also replace with P0. So we're going to get P1 minus P0 plus P0. And so it becomes P1 minus P0, and therefore it's idempotent. The next thing we need to check is whether we take this symmetric idempotent matrix P1 minus P0 and multiply it by the design matrix, multiply it by the mean vector for y, do we get 0? Remember, this is one of the things that has to be true in order for something to have a chi-square distribution. Okay. So if we do P1 minus P0 times the mean vector under the null hypothesis, and remember, whenever we do these calculations, we're doing these distributional calculations, we're doing it under the assumptions of the null hypothesis. This is P1 minus P0 times X0B. Now this is maybe a bit of an abusive notation. I'm defining B here to be the vector. So for example, in the grandparent example, B would just be B0, B1, B2. So we're using B. B is playing multiple roles here, but we can know what that means by the context. So B has to have the same number of elements as the number of columns of X0. Okay, writing this out, we get P1 X0B minus P0 X0B. P0 X0 is clearly going to be X0 because P0 is the projection matrix onto the span of X0. So the columns of X0 are already in the span of X0, and therefore if we project them onto that span, we get them back. So that thing is true. Now let's look at P1 X0. We know that X0 is in the span of P0. Well, we just said that. We also know that the span of P0 is a subspace of the span of P1 because P1 was constructed from the full design matrix, which contains the columns of X0. And therefore, if we project onto the column space of X1, the full design matrix, we're going to get X0 back as well because these vectors are used in the construction of the span of X1. They're a submatrix. Okay, so that shows if we get X0B minus X0B, which is 0. So that satisfies that assumption as well. Next thing we need to check is the rank. That will tell us the degrees of freedom in chi-square distribution. Rank of P1 minus P0 is equal to the trace because they're symmetric and idempotent of P1 minus P0. And this is just the trace of P1 minus the trace of P0, which is the rank of P1 minus the rank of P0. And because the column space of x1 is the same as the column space of P1, the rank of P1 is the rank of x1. And because the column space of x0 is the same as the column space of P1, the rank of P0 equals the rank of x0, which is exactly the model degrees of freedoms. So we get that the rank of this difference is the difference in the model degrees of freedom, which is exactly what appears in the numerator. So in the numerator, we get RSS 0 minus RSS 1 divided by this difference in degrees of freedom. So we showed that this thing can be calculated. RSS 0 minus RSS 1 can be calculated as y transpose P1 minus P0y. And we verified that matrix P1 minus P0 is symmetric, idempotent, and when you multiply it by the mean vector, you get 0. And therefore, if you divide this by its rank, you get a chi-square distribution with this number of degrees of freedom. Okay, the last thing we need to check is that the numerator and the denominator are independent. Now, if we look at let's look at each of these two things. So in the numerator, we have RSS 0 minus RSS 1. This is a function of P1 minus P0y. The reason for that is you can write y transpose P1 minus P0y as y transpose P1 minus P0 times P1 minus P0y. So that is just the squared length of P1 minus P0y. So RSS 0 minus RSS 1 is the squared length of this vector. RSS 1 is going to be the squared length of this vector. Those properties follow because this is an idempotent matrix. Both of these things have expectation 0 under the null. And so this is multivariate normal. This is multivariate normal. So if we check that the covariance between these two vectors is 0 under the null hypothesis, then any function, then they're independent vectors, and any function of them are independent as well. And then that will show that the numerator and the denominator are independent. All right, so let's look at that covariance. These have mean 0. So the covariance between them is just the expected value of the first one times the second one transpose. We pull out this thing and this thing. We get this times expected value of y transpose, which is this quantity. And then still have this on the right. And if we collect terms here, we can do, let's say, do this one first. This is P1 minus P0 x0 times BB transpose x0 I minus P1 times sigma squared. This should have a sigma squared here. P1 minus P0 times I minus P1. Okay, so here we already said before that P1 x0 is x0 and P0 x0 is x0. So this part is going to be 0, so it doesn't matter what you multiply it by, that's going to be 0. And then this one is going to be P1 minus P0 minus P1 times P1 plus P0 P1, and we already checked that this is, we already checked, so this is P1 minus P0 minus P1 P1, this is going to be P1. And we already showed before that P0 P1 is P0. So we end up getting P1 minus P0 minus P1 plus P0, which is 0. So therefore, these two vectors are independent vectors, and the numerator, which is a function of the first vector, is independent of the denominator, which is a function of the second vector. Now, one note here. If we think back to what we did in the proof depended on the fact that the span of the design matrix for the null model was a subspace of the span of the design matrix for the full model. So that we use this fact to show, for example, that P0, P1 is equal to P0. So these F-test results will only apply to comparison of models that are nested, which means that the null model is a special case of the alternative model. So the example that we've used is one of those cases. So remember, the null model or the reduced model is yi equals sum j equals 0 to 2 xij bj plus epsilon I, and the full model was sum j equals 0 to 6, which includes the grandparents. Okay, now in general, we can write down these hypotheses in the following form. If we can write the null hypothesis as this system of equations, some matrix K times the regression coefficient vector equals some vector M. And here's a bit of unfortunate notation. This is a lowercase k. This tells us how many equations we have, and this is the capital K that they use in the book. So the example we've been using throughout this module can be written in the following form, where this is K transpose, and this is the regression coefficient vector. So if you think about what are the equations are going to be 0, 0, 0, B3 equals 0, 0, 0, 0, B4 equals 0, blah, 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 B5 equals 0, and blah, 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 B6 equals 0. You can also write the t-test hypotheses in the same form. So here there'll just be one equation. So this is an example where C, the coefficient vector in the t-test, is 0, 0, 1, minus 1. And this hypothesis corresponds to this function of the parameters. So we can use an F-test to do things that we could use a t-test for as well. So the F-test is more general than the t-test. And then one final thing, turns out we can write the difference in sum of squares that appears in the numerator in the following form. So we'd get the estimator for the regression coefficients in the full model. We multiply that by K transpose, and we subtract off its hypothesis value. And then you have this matrix in the middle, which is the covariance matrix for K transpose B hat, and then you have this thing on the end. So this is a quadratic form, and it turns out you can write this difference in residual sum of squares in this form. So maybe this is more natural to you. So we're estimating B hat, and we're checking whether it's close to M, and we're using this function of the difference to check how close it is to the hypothesized value. So we're not going to derive this, but there's a reference in the textbook for this.